You probably know we transmit all our messages on the internet in ones and zeros, and it's kind of like a Morse code. Imagine beeps going around the world. These are our ones and zeros. What happens if something goes wrong? Right? When you're transmitting a message, a 1 turns into a 0, or 0 turns into a 1, which means the other person receives the wrong message. Well, how can we fix this? Well, we're going to fix this by turning your message into code words. That's what they're called, code words. And these code words are a bit more distinct from each other. The idea is kind of like the phonetic alphabet. Have you ever tried spelling out like a word or a name using the phonetic alphabet? That's the Alpha, Bravo, Charlie thing. The reason you do that is because when you're spelling out a word, the letters kind of sound a bit similar, they can get confused. The letter B might be confused with the letter D because they sound similar, but then Bravo is less likely to be confused for Delta in the phonetic alphabet. So it helps you transmit messages without mistakes. So let's say we're trying to transmit something like a coin toss. Right, heads or tails. When I get a head, I'm going to transmit a 0, and if I get a tail, I transmit a 1. But when I'm transmitting the result, a mistake might happen. So just to be sure, I'm going to transmit 0, 0, 0. If I get a tail, I transmit 1, 1, 1. Then it's less likely that I'm going to get a mistake here, because if a mistake happens, for example, if I got something like 1, 0, 0 at the other end, you know something's gone wrong, because I'm expecting one of these answers. So something's gone wrong. Now, I don't know which one it is, but I would say it's more likely to be heads, because there's only one mistake for it to be heads. If it was tails, that would be 2 mistakes. So I might interpret that as heads. In the same way, if I received 0, 1, 0 or 0, 0, 1, I would say those are heads. If I received 0, 1, 1 or 1, 0, 1 or 1, 1, 0, I think they're more likely to be tails. So that means that this list on the left gives me all the messages that I'm going to reinterpret as heads, and the list on the right gives me all the messages I reinterpret as tails. So it helps me fix mistakes. Well, we can actually think of this geometrically. Think of these zeros and ones as coordinates. Coordinates in 3-dimensional space. So let's say this one down here is 0, 0, 0. And then this one would be 1, 0, 0. This would be 0, 1, 0. And if I go up, 0, 0, 1, and let's just fill in the coordinates we've got here. 0, 1, 1, 1, 1, 0, 1, 0, 1, and up here, this is 1, 1, 1. So all the possible messages become points in 3-dimensional space. Now imagine we have a sphere centered on those code words. So let's have a sphere centered at 0, 0, 0, and another sphere centered at 1, 1, 1. And let's say the sphere has radius 1. That means that these messages that are closest to heads are all contained within that sphere. So a message that is contained within a sphere is interpreted as the code word that is at the center of the sphere. Now, it would be nice if we could fit more code words in. That means we could transmit more information. Not just heads and tails, we could transmit more things. So the more code words we can fit into that space, right, the more things we can send. I might use instead as my code words 0, 0, 0 again. Let's use 0, 1, 1, 1, 0, 1, and 1, 1, 0. So I've got 4 code words, they're packed in a bit more densely. But the problem with that is, if I use those as code words, if I have a mistake, if I had then 1, 1, 1, which would be a mistake, it's actually quite close to 2 code words. So I don't know which one to pick. Although I can tell there's a mistake that's happened, I don't know how to reinterpret the mistake. Now, that is a more dense packing though, so that is nice. In fact, if you extended that packing there forever, you get hexagonal packing, which is the densest packing possible in 3 dimensions. But let's try another way of sending 4 code words. So I'm rolling a tetrahedral die, I'm trying to send the result, and I'm going to either get 0, 1, 2, or 3. 0 is going to be transmitted as 0, 0, 0, 0, 0, so 5 digits. I'm going to have 1 be 1, 0, 0, 1, 1. 2, I'll transmit as 1, 1, 1, 0, 0. And 3, I will transmit as 0, 1, 1, 1, 1. So they are 5 digits long. They are coordinates in 5-dimensional space. So these would be our code words as points in 5-dimensional space. And then imagine them surrounded by a 5-dimensional sphere as well. So if you get a mistake then, let's say I get something like 1, 1, 1, 1, 1, it would be closest to 3. That would be reinterpreted as 3. Actually, I'm going to kind of draw this out just to show you what it kind of looks like. It's going to be two-dimensional, of course. So these are going to be our code words. So let's say this is 0 here. This is a point in 5-dimensional space surrounded by a sphere. That's a 1. That would be code word 2, and this would be code word 3. This is only a 2-dimensional slice of what I've done there, but this is not the densest packing possible. Let's see what is the densest packing possible. First of all, what's the density of this packing? Let's just treat it as circles here. If this extended forever, we would have a packing of circles. Let's just create a unit that I can repeat over and over again, and then that will be the full packing. And if I can work out the density of this unit I've made, then I've worked out the density of the packing. So I've made a little square here, and if I just repeat that square over and over, that means I get the whole packing. Well, that square contains one circle. So the area of that circle, it's pi r squared, isn't it? Let's say it's radius 1. So I'm just going to say the area then is pi. And what is the area of the square that I've created? Remember, these are circles with radius 1, so it's just 2 by 2. So that's going to have an area of 4, and the density is going to be the area of the circle divided by the area of the square that contains the circle, pi over 4, which is equal to 78.5%. So that's the density there, and that's not the best density. We can do better than that. You might be able to see we can do better than that. A better one would be this. We have the circles here, and then we can fill that kind of dimple there. So we've got this kind of packing that would go on forever. I'm just going to split it up with using this parallelogram that is containing one complete circle, just like before, and it will have an area of pi. And now we're going to look at I'll just call it a box. That parallelogram, what is the area of that? It has a base of 2 multiplied by the height. With a bit of Pythagoras, that's going to be square root of 3. So the box has an area of 2 times the square root of 3. And then the density. We divide one by the other, which is equal to 90.7%. Much better, much more dense. So if you can pack in these code words more densely, you're going to be able to fit more code words into your space. So that is the best density for circles. Let's have a look at other dimensions, because we're going to have to use higher dimensions for this idea. Let's have a look what the best possible packing is in all the dimensions that we know of. So in dimension 2 is what we've just done, pi over 2 root 3, the 90.7%, proven to be the best possible by Feyesh Tot in the 1940s. Dimension 3 is pi over 3 root 2, which is 74.1%, which was proven to be the best possible by Thomas Hales in the 1990s. The best we found in dimension 4, pi squared over 16, that's 61.7%. In dimension 5, pi squared over 15 root 2, 46.5%. In dimension 6, the best possible is pi cubed over 48 root 3, which is 37.3%. For dimension 2, we've absolutely proved it. Dimension 3, we've absolutely proved it. The ones I've shown you so far, best known, 7 is pi cubed over 105, which is 29.5%. And now in dimension 8, the best known is pi to the 4 over 384. The density of that is 25.4%. In 2016, this was proven to be the best possible by Marina Vyazovska, not that long ago. And that's because in dimension 8, there is a particular structure, it's called E8, it has a name, where the gaps become big enough that you can start to fit in extra spheres into those gaps. And then the structure becomes rigid again, and then you get this properly dense packing. But it's also been proven to be the densest possible, including regular and irregular packings. When they did that, they very quickly then showed that you can do the same thing in dimension 24. And in dimension 24, they showed that the best packing is pi to the 12 over 12 factorial, 0.19%. And that structure is a regular structure called the Leech Lattice. And John Leech, who came up with this Leech Lattice in the 1960s, was actually studying error-correcting codes when he discovered this structure. But it was Marina and others that showed that this structure was also the densest possible in dimension 24.
In dimension 24, that's not very dense, is it?
It's not dense, it's not very dense. However, we do use dimension 24, the Leech Lattice, or E8 in dimension 8, we do use those structures in error correcting codes that we use today to transmit our messages. Yeah, so every message is transmitted with this kind of idea. I was talking about rolling a die or just sending heads and tails. But yes, if you're sending a message on the internet, so you're sending an email, so the letters of the message gets turned into a number, which is not that complicated. A is 1, B is 2, Z is 26. And then you transmit that number. Now you could just transmit that as a binary number if you want to, which is kind of how ASCII works. Or you can use this bit of a code word idea, have a bit of extra redundancy in there, just so that mistakes don't happen along the way.
So this was the third part in a trilogy of Sphere videos, and they were brought to you by Brilliant. Brilliant is an excellent site. It's full of puzzles and quizzes, all about science and mathematics, computer science, all designed to really help improve the way you think. But one of my favourite things on the site are their problems of the week. Have a look at these. These are just for 1 week. You can see there are beginners, intermediate, advanced. You can try and answer them, but you can also go down below to a discussion in the community all about the problems. It's really great. Go to brilliant.org/numberphile to have a look at the site. There's loads of free stuff, but if you use that URL /numberphile, you can also get a 20% discount on their premium service, which unlocks all the good stuff. I'll also include a link in the description to the problems of the week so you can check them out. Our thanks to Brilliant for supporting this trilogy of videos all about spheres.